Hello everyone, my name is Ewell Kubrat and I'll be presenting about the lower bounds for algebraic decision trees. So what is the problem here? So are there lower bounds to how fast an algorithm can run? These are just questions that we're asking. What are the minimum number of steps that an algorithm needs to take to solve a problem? And also, in the realm of algebraic decision trees, what is the minimum length or the minimum depth for an algebraic decision tree to solve decision problems that require the yes, the no problems? And so there's a famous problem called the element distinctness. So given n numbers, are all the n numbers distinct? So we're going to be using comparison-based um, models for solving this problem. And also the other problem is that how many tests do we need, or how many questions do we need to ask in the decision tree to actually um, determine element distinctness? So why is the problem important? So it actually helps us in designing algorithms. So if we know to until a point of how that algorithm can be optimized, so we cannot move beside that point. So it could help us know our limits. So if our algorithm cannot do better than a specific point, we'll just stop and look for other solutions. So the lower bound for comparison-based sorting is omega of n log n, as we all know it. It also proves that an algorithm cannot perform better than the lower bound that it's set by the model. It's regardless of the computing power of the machine. So 50 years from now, this model is still going to hold from now. Its applications in machine learning, for example, in training neural networks, you'll give it input data and to check the duplicates in that input that we can definitely use this model. Okay, so what is the solution? We can see this from a different angle to see the geometry or the shape of the problem to solve the problem. So we can model a given input and inputs on an n-dimensional space. If we've given three inputs, we can imagine it as a point in three-dimensional space. And so when comparing two numbers, when we're running the algebraic equations, we can just um, draw a hyperplane on their equality. So later on, when the algorithm runs, if that point lands on that plane, it makes it sure that there are duplicates. So the question is that we need to um, slice the n-dimensional space into enough splits so there can be unique zones to be identifiable. So they've still anyhow they found that there needs to be at least n factorial distinct rooms or distinct yes zones to determine if the given array or the given inputs are duplicates. So in the decision tree, we just ask these polynomial equations that are actually quite advanced in some cases, but we asked polynomial equations to check them. So we asked three questions. Based on the output of the three questions, we're going to have a decision tree. So they say that we need to at least to have 3 to the power of h um, leaf nodes at the end, yes leaves to be accurate. And so this implies that the height of the tree is going to be n log n. So the lower bound for the algorithm decision is going to be n log n. So let's check it with an example. Given three numbers, one, two, three, three this is how the algorithm runs. It just checks one and two. So if one and two are one is less than two, so it goes to the left because it's true. It checks one and three, and one is a difference, so it goes um, to the left again. And so as soon as it goes to the left, if it's true, then it hits a yes. And so um, we basically found out that this array um, is distinct. And also, when asking each question, we are actually drawing hyperplanes um, in the n-dimensional model. So each question, x minus z greater than 0, is actually drawing x equals to z plane in the n-dimensional space. So this is theoretical Lorentz, so it was purely experimental. So Benner also in 1983, he proved that Any comparison based algorithm cannot be the omega n log n lower bound for the Algebraic distinctness problem. Still, this problem has not been optimized beyond that point, so this theorem still holds to this day. And also, Steele and Liao also showed that for the knapsack problem, the lower bound is omega of n squared, and for the convex sub problem, they showed that the lower bound is omega of n log n. These are the references that we used, two papers, and the other links are just for images. So as a conclusion, we can conclude that we should know the mathematical limits of computation, right? So we cannot go beyond a certain point in our algorithm. So a question's algorithmic or the geometry of a question unlocks its algebraic bounds, and the omega n log n for element problem still holds till now. And one critical point is that in a decision tree, even though we give it complex polynomial text so that we can draw curvy lines or some special planes in the in n-dimensional space, some problems are still require they do still require a minimum amount of computation, and they can't simply be optimized further. Thank you.